Welcome to the High Energy Density Science Center Seminar Series. I'm pleased to have with us today Dr. Brian Applebe of Imperial College. Dr. Applebe is a researcher at the Centre for Inertial Fusion Studies at Imperial in London. He obtained a bachelor's degree in engineering from the University College Cork, Ireland in 2006 and a master's in mathematics from the same institution in 2007. He was awarded a PhD in plasma physics from Imperial College, London in 2011 for work on MHD modeling of gas puffs. And since then, he has worked in the Center for Inertial Fusion Studies on a variety of problems in HEDP, including neutron spectroscopy, pulse neutron sources, ICF theory, plasma transport theory, and he's a visiting scientist at Sandia National Laboratories and Los Alamos National Laboratory. So please be aware that this seminar is being recorded. So if you are uncomfortable with that, please log off. And also, if you have any questions, please enter them in the chat field, and I will read them at the end. And also be aware that, of course, this is an unclassified meeting, and we also have external researchers that are logging on. And of course, our speaker is from another institution. So please be aware of any export control issues. Otherwise, I hope you enjoy Dr. Applebe's talk, and I'm very much looking forward to it. Thank you very much. Brian, please take it away.
Okay, thank you, Paul, and thank you for the invitation to speak here. It's a shame that I have to do it remotely and I'm not able to give the talk in person, but I do hope everyone is keeping safe and well in these under the circumstances. Okay, so the title of this talk today is Investigating the Physics of Burning Thermonuclear Plasmas. And essentially what I'm going to do is give an overview of something that we've been working on for probably the last couple of years, whereby we've been thinking about, you know, what physical processes of interest might occur if you had a burning thermonuclear plasma, and could they be important? But what I want to do to start is I just want to give a quick introduction to the Centre for Inertial Fusion Studies where I'm working. This is based in Imperial College London, and essentially we are a group of researchers doing theoretical and computational research of ICF and high energy density physics. It is based in Imperial College London. It's jointly funded by AWE. And so the co-directors are Professor Jeremy Chittenden and Professor Stephen Rose. And we have approximately 10 researchers then working in the group. And I've just listed here some of the kind of the main topics of focus of the group. And that is quite a lot of 3D Rad Hydro and MHD modeling. We run the code, Chimera and Gorgon codes for that. And what you're actually looking at in the bottom right-hand corner perhaps is my video. If I move the video over here, what's in the bottom right-hand corner of this slide is a movie of a 3D Chimera simulation of an imploding ICF capsule. So that just illustrates, you know, some of the work that we do. What we also spend quite a lot of time doing is the modeling of nuclear diagnostics relevant to ICF. So in particular, that's neutron diagnostics and gamma ray diagnostics. So trying to understand what information one can obtain from those diagnostics and how they can improve our understanding of ICF implosions. And also we do quite a lot of work in atomic and radiation physics and in Vlasov-Fokker-Planck modeling. So that's, you know, our kind of general areas of interest. Some of the particular topics that we're working on at the moment, so these are largely PhD students that are working on these and you know, some postdoc work. These include the MHD modeling of MAGNIF experiments, extended MHD modeling of MAGLIF, and I'm going to touch upon these two topics later on in this talk. Also some advanced grid development techniques for our codes. Also 3D CBET modeling is a project that we've recently started for, you know, being able to look at the laser drive in ICF in more detail, and also some equation of state and opacity modeling. So that's the, I think the things that, you know, these are probably represent the topics that we have been most actively working on since the lockdown started. So hopefully, you know, by the time everything gets back to normal, we'll have made lots of progress with all of these. And one final topic that I'm showing here, that is something that I have been working on quite closely with Aidan Crilly, is a particular example of our synthetic nuclear diagnostics work. And in this case in particular, it is modeling of neutron spectroscopy from ICF implosions. So we have spent quite a lot of time trying to understand what new information can one obtain from the neutron spectra that you can measure in an ICF experiment. And this just shows an illustration of some of the results that we've come up with. So what you're looking at in the top slide, or in the top diagram here, is just a neutron spectra from a simulation of an ICF implosion. And there is actual experimental data here in the bottom right of this particular region of the spectra. And what we have been looking at is ways that we can access this particular feature of the spectra here, which is a backscatter edge of neutron scattering of tritium, in order to measure novel physical quantities. So in this particular example, we have established a technique for measuring the temperature of the cold fuel in an ICF implosion by analyzing that feature in the neutron spectrum. So we've been applying this technique to experiments from the Omega laser, and we are thinking about, well, how we might be able to apply that technique to NIF experiments. Okay, so that essentially gives you an overview of the different things that are going on at CIFS. However, the thing I want to talk to you today about is something quite different, and that is some work on burning plasmas, of what may occur if we had a burning plasma, some novel physics. And essentially, there are two main results that we've come up with in this regard, which I'm going to talk about. And the first of these here is a model for what happens when you have a flux of alpha particles interacting with electrons in a burning plasma. And the second one is going to be looking at some of the magnetic field transport effects that can happen in propagating thermonuclear burn. So that's if you have a magnetic field for some reason in the plasma, when it ignites and burns, then the effect that magnetic field can have on the burn. So basically, for the remainder of this talk, I'm going to be working through these two different topics and trying to illustrate, what we think the interesting physics is. And just to emphasize, the technical details of what I'm going to discuss is mostly covered in these two publications. So the first one is from Physics of Plasmas 2019. The second one here is on archive, and it should be appearing in Physics of Plasmas quite shortly. But what I'm going to start off with is just a sort of a general introduction to, burning plasmas and the underlying physics that, essentially makes burning plasmas interesting. So to start with that, I have this set of results from a 1D Rad Hydro simulation of an igniting ICF capsule. And I suppose at this point, it might be appropriate for me to say that, we recognize that we are picking nice problems here. I'm not going to discuss anything about how one can actually reach the state of a burning plasma. I'm essentially assuming that has been achieved, and then looking at what physics might result from that. So, you might argue I'm sidestepping all the more difficult parts of ICF, but nevertheless, we think there's something interesting to looking at these regimes. And certainly, a burning plasma is really a unique plasma environment that, would behave very differently to any other plasma that we can create in the laboratory. So it's worth thinking about, what that uniqueness might entail. So with this particular plot, what you're looking at is the results from a Rad Hydro simulation. In the top set of diagrams are temperatures and densities. So the red lines are the ion and electron temperatures. The black line is the density of the DT fuel, and the purple line here, the magenta line, is the density of the carbon ablator material. And so there are 5 snapshots in time here covering about 200 picoseconds during burn. And this is really, the thing to take from this is it's a strongly igniting and burning plasma. So you can see the temperature is increasing throughout these 5 snapshots. It's reaching almost 20 keV by the final time. And you can see that it is burning out into this, what initially is a cold, dense fuel layer of DT. Our temperature profile is essentially burning out into that dense fuel layer. So we're propagating the burn from a hotspot into a layer of dense cold DT fuel. What is shown in the bottom is the power balance for the particular, snapshots in time. So there are 4 different sources of power balance here. There is the alpha heating term, there is electron thermal conduction energy transport, there is radiation losses in blue, and then finally there's the PDV work being done on the capsule as well. So essentially what you can look at as positive values here correspond to our fuel gaining energy, negative values are losses from the fuel. And really what I am, there's kind of, with this slide, there's 2 main observations, I think, to make that show why this is an interesting regime for plasma physics. First of all, we can see that the physical quantities have extreme gradients in time and space. So clearly this is only 200 picoseconds in which your temperature is increasing rapidly, but also, and I think possibly kind of more importantly, is the fact that, you go from a temperature of 20 keV to, less than a keV over essentially, less than 100 microns. So those temperature gradients that you get are, extremely large. And they mean that, we can't treat this burning plasma as, some sort of homogeneous plasma. We have to think about what the spatial effects might lead to in terms of transport processes. And then the other, observation is that this might seem trivial, but, I think it's worth making, is that there are significant energy exchange processes happening as the plasma burns. So the most obvious example, and the one that's relevant for what I'll be dealing with in this talk, is the idea that you're producing a huge amount of alpha energy that is then rapidly being redeposited into the fuel. So, that exchange of energy between the alphas and the fuel, what is the physics that underlies that? And do we understand that physics correctly? And one can ask similar questions, for say, the radiation effect, thermal conduction, all these energy processes. So this is...
So, Brian? Just a couple questions for Sheffield. What is T naught and S?
T naught here, I think, is essentially so this is a scaled implosion from NIF, and I think the S represents the scale factor, which I would have to look up. It's in this publication from John Tong. So I would have to look up what value S has in this particular implosion. And T naught, I think, is the time of maximum compression.
Great, thanks.
Okay, so this is a macroscopic picture of, what the dynamics of a burning plasma. Underpinning this then is a whole bunch of microphysics, as illustrated by this particular diagram. And I've taken this diagram from a publication by Steve Rose from last year in this is Philosophical Transactions of the Royal Society A, where he listed out a general list of the physics that could be occurring in a burning plasma. And so he has shown all these different interactions that we could have happening in the plasma when it burns, and how the different species and different processes all interact with each other. So really the question that I'm interested in is, well, do we understand these processes with sufficient precision to ensure macroscopic models are accurate? So we can look at all these microphysics processes in, hopefully in isolation, in theory, in experiments more difficult. And we can ask, well, do we know how these microscopic processes work such that we can have a rigorous model for them in the macroscopic models? So, obviously there is quite a lot of different interactions going on here. It's probably worth highlighting that, Steve has been very comprehensive in this, and so he has also included high Z dopants here, which is what the X represents, which means essentially that we can have bound electrons to consider in the interactions as well. So the general problems that we've been thinking of revolve around, well, do we understand this with sufficient accuracy such that we can trust what we get from our radiation hydrodynamic models? Also, more generally, I think, is that we can also think a bit about, well, is there any interesting physics that we can do if we did have a burning plasma? So again, this is taken from Steve's publication, and essentially it's a list of all the either challenges. I've said challenges here in this slide, but one could also consider some of these would be possibilities that, these are the physics processes that are occurring in a burning plasma. There is, which I've just been dealing with, do we understand them sufficiently well, such that we can trust their macroscopic models? But there's also, within this list here, there are some things that really it's a case of, well, if we did manage to achieve a burning plasma, we could do interesting physics in that regime. So I'm not going to go through them in detail, but essentially you can see that the extreme conditions here, such as a high areal density, high radiation intensity, high electron temperature, high ion temperatures, high alpha flux, high neutron flux, each of these things that we can generate, and really we can generate a unique capability, capacity in, say, ICF plasmas. They all generate then physics that we could study using the burning plasma. So what I am particularly interested in is kind of essentially focusing on one of these specific things and also adding to the list. So first of all, what I'm going to be focusing on is how the alpha flux could lead to non-equilibrium populations of electrons in the plasma and what effects that might have. And also what I'm adding to the list here is that we should also consider what magnetic fields might do in a burning plasma. So we can say, well, if we understand all these different processes in an unmagnetized plasma, then do we think we understand them if there was a magnetic field present in that plasma also? And there is quite a lot of contemporary motivation for doing that, for looking at the magnetic fields, particularly for these two experiments that are being investigated at the moment. First of all, there is John Moody is looking at the idea, and John Moody's group are looking at the idea of magnetically assisted ignition, in which a coil is wrapped around the hole ram for indirect drive ICF, and essentially then that coil will generate a seed field of the order of tens of Tesla within the capsule. When the implosion takes place, then that field gets compressed with the imploding capsule, such that when you reach stagnation conditions, you should have quite a large B field present in your compressed plasma. And there is also magneto-inertial fusion, which is being investigated at Sandia National Laboratories, which is where a cylinder of DT fuel is compressed and it has a magnetic field entrained in the fuel as it is compressed. So both of these experiments kind of fall under the category of magneto-inertial fusion, whereby you're adding a B field to assist you with reaching ignition conditions. And there is essentially two reasons why we want to do that. The B field is going to reduce electron thermal conduction losses from the fuel as it's imploding. So essentially, magnetic fields actually insulate fuel. So that means we should be able to minimize the energy we're losing during the implosion. And the second reason is that if the fields are sufficiently high, then they can confine the alpha particles within the fuel in order to, ensure that those alpha particles can actually heat fuel and they are not lost to ablator material or liners or whatever is surrounding the fuel. So these represent two very good reasons why you should include magnetic, why it's good to include magnetic fields to try to achieve a burning plasma. But what we're interested in, and which has been not investigated as much, is, well, and just going back to the previous slide, what effect could this magnetic field have when you would create the burning plasma? So these two reasons here are really just two reasons that will help you achieve the burning plasma state. But from then on, we really don't know what the effect of a magnetic field is. And then finally, the other, say, motivation for, considering what effect B fields might have is looking at conventional ICF and the fact that, even if we do not attempt to, add a magnetic field to our imploding ICF capsule, we might generate magnetic fields during the implosion through this Biermann battery process. So I've listed the equation for the Biermann battery process here, and essentially what it tells you is that if you have gradients of temperature and density that are not parallel, then essentially that it sets up essentially electron vortices within the plasma, which can generate a magnetic field. So what I'm illustrating is a result from Chris Walsh from a couple of years ago, where he essentially took this Biermann battery term and looked at an imploding ICF capsule and calculated how much field should be generated by this Biermann battery effect. So you're seeing the results of his work here. The left-hand side represents a density map of an imploding ICF capsule. And in a sense, this has been perturbed with a whole range of different perturbation modes that generates all these fingers of cold, dense material pushing into the hotspot. Now, essentially, all those perturbations act as a really good source of regions where your temperature and density gradients are not aligned, and so their Biermann battery is quite strong. And what is on the right-hand side here is the magnetic field that is being generated due to that Biermann battery. So we can see that essentially this scale here is in Tesla. It's going up to 10,000 Tesla. So in this calculation, you're generating pretty significant magnetic fields, even though you didn't intend to, and we're not trying to use those magnetic fields to assist with our implosion. So this is evidence that perhaps we should be considering what effect B fields might have, even for platforms where we are not trying to achieve ignition using magnetic fields. Okay, so that kind of essentially lays out the field, I guess, in which we've been thinking about these problems. What I'm going to do now is move on to the first, say, insight that we have gained by looking at these problems. And that is the interaction of alpha particles with electrons. And at this point, I should note that in the particular work that I'm going to be discussing, I should acknowledge these collaborators who I've been working with. And that includes, I guess I should highlight Mark Sherlock and Chris Walsh, who are both at Lawrence Livermore. Okay, so to set the scene for this particular point, we can start off, and we know in our burning plasma that we have a large alpha flux. Our plasma produces a large amount of alphas. Then the gradients in time and space mean that the net flux of alphas can be quite substantial. What a lot of research has gone into is looking at how those alpha particles will slow down in a background, thermal population of electrons and ions. And so the details of the stopping power of fast ions, such as alpha particles, has been quite well studied. And in particular, there's molecular dynamics simulations and PIC models for fast ions that show that there's this really rich electron dynamics that you can generate from those ions slowing down. So that you get these sort of wake structures behind the fast ion particles. So I'm showing one example on the right here, which is an image I've taken from this paper by Zhao et al. From 2015, which is showing the stopping of an ion beam in a magnetized plasma. And really, this is just an illustration of this really nice wake structure that you get in the electron density maps from that particle slowing down. So we know all this rich dynamics exists. However, usually when we do an integrated macroscopic simulation, so this could be a Rad Hydro or an MHD model, we don't include these effects, and we say, well, look, this wake structure is occurring on time and length scales that are much, much smaller than the time and length scales that our MHD or our Rad Hydro is evolving on. So therefore, we don't need to worry about this. We can say that essentially because the electron-electron collision time and the electron-ion collision time is so much faster than the slowing down time of, say, the alpha particle, then, we don't need to worry about these wake structures, and we can assume that our electron population remains in a thermal state, described by a Maxwellian distribution function. And so what that then allows us to do is we can say, well, we'll take the stopping power model that we calculate using theory or using molecular dynamic simulations, and we then can just conserve energy between slowing down ions, to work out how much thermal energy we add to the fluid. And so the question we ask is, well, is this okay? We focused on the electrons in particular because there has been some work to show that, well, kinetic ions have moderate perturbations from Maxwellian by alpha particles, but, we don't think this is significant. So people have looked at the ion scenario, but the electron one is less well studied. So our approach to this has been essentially to look at a VFP model for the electrons in the presence of an alpha population. So I've just written the VFP equation for the electrons there. I should say we're assuming throughout that it's a weakly coupled, non-degenerate plasma. So, we're working in kind of ideal conditions, but nevertheless, we feel that that's a good starting point. So by making some assumptions, then we impose a fast ion flux. We assume we know what the alpha population is. We also assume that because the electron-ion collision time is much, much faster than the alpha slowing down time, then we can assume steady state local behavior for the electrons. And essentially, we can apply a Chapman-Enskog theory to our electron population. And with that, we are then solving this linearized version of the VFP equation. And essentially, what that gives us is it allows us to calculate what the perturbation on the electrons is due to this flux of alpha particles. And here, essentially, I'm just illustrating some of the results that we get. The dotted black line here is just showing you what a Maxwellian distribution looks like in units of particle velocity normalized to the electron thermal velocity. And we then have imposed alpha particle, which is a velocity that's about half of what the electron thermal velocity is. And essentially what we get is this blue line represents how that Maxwellian population of electrons is perturbed. Now, this isn't scaled correctly. This is a very small perturbation, so it's really just a small bump on this Maxwellian distribution. But nevertheless, we are getting this perturbation of the electron population due to the alpha flux. Again, what we're particularly interested in is in the magnetized plasma case. So we can look at the solutions to the same equation, but by also imposing a magnetic field. And just some housekeeping here is that when we look at these magnetized scenarios, first of all, we have a coordinate system for magnetic field transport where we talk about the perpendicular and wedge components. So perpendicular in our case will represent some component that is parallel to the alpha flux. So it's orthogonal to a magnetic field into the page here. And then the wedge component is orthogonal to both the alpha flux and the magnetic field. So in our case, wedge will be directed downwards. And also for most of the remainder of the talk, I won't be discussing magnetic field strength, but instead we'll be using this electron Hall parameter, which essentially tells us, well, what the effect of the magnetic field on the electrons is. So I use either chi or omega tau to represent the electron Hall parameter. And essentially for small values of electron Hall parameter, we can sort of say that the collisions of electrons dominate, whereas for large omega tau, large Hall parameter, it is the B fields, the magnetization effects, which dominate. So with that housekeeping in mind, we can look at the same results for our Vlasov-Fokker-Planck equation for electrons in the presence of an alpha flux. And what we see here essentially is that we are generating populations, we're generating perturbations of the electron distribution function in both the perpendicular direction and also in the wedge direction. Okay, so the red line here, in this plot here, represents how we are perturbing the component of our electron distribution function orthogonal to both the magnetic field and the alpha flux. Now, in order to make that useful for our macroscopic models, again, the idea that we're, the basis of what we're working on is we're trying to figure out, well, what physics from the microscopic picture might be relevant for a macroscopic picture. So we can say, well, on the kinetic level, we see that the electron population has been perturbed. Can we turn that into a useful quantity for our, say, Rad Hydro or MHD models? And so we can do that by taking moments of these perturbations of the electron distribution function. So that's what we're doing here. We can essentially do things. We can take the third moment, which tells us how the perturbation of electrons can be modeled as an electron current term, or we can take the fifth moment if we wanted to calculate what the electron heat flow was. And so that's a process that we've worked through. And essentially, this is the results that we come up with for the electron current moment. So what I am showing here is on the x-axis is just our Hall parameter on a log scale. And then on the y-axis is the current that is induced due to the alpha flux generating a perturbation of the electron population. And in particular, we've decided that the neatest way of doing this is to, okay, sorry. So the neatest way we can do this is by essentially defining this thing we call the collisionally induced current, which is the sum of the alpha current and the electron current moment that the alpha flux generates. And essentially, we've got two components to that. We've got the perpendicular component here, and we've got the wedge component here. And again, this is a function of the electron Hall parameter. And there's essentially three regimes for this that we can see. First of all, at low Hall parameters, so this is where collisions dominate rather than magnetization, essentially the alphas move through the population of electrons, and they are dragging some electrons with them such that we get a net collisionally induced current that is in the opposite direction to the alpha flux. When we go to intermediate values of the Hall parameter, this is where the wedge term dominates here, whereas the perpendicular term is close to zero. And so what we are left with is this, we generate almost zero current or parallel to the alpha flux, but orthogonal to it, we have a net current. And finally, at very high magnetizations, essentially the magnetic field effects on the electrons dominate. And so there is no significant electron current. And so the collisionally induced current is really just the alpha current itself. So we see these regimes, but the important point here is that we can say, well, even with, by essentially not having any MHD model in our code, we could be generating these currents just by having a population of alpha particles being produced within the plasma. So the alpha flux itself, by the alphas colliding with the electrons, that is sufficient to generate an electron current within the plasma. And in fact, we can kind of make some estimates that may be kind of quite significant. So I'm going back to this plot that I showed towards the start of this talk. However, now what I've done is I've also, on the bottom here, I'm just listing the peak alpha flux that we get in this simulation is about 10 to the 35 particles per square meter per second. Using the model that I've just been showing you, we can calculate that gives us a collisionally induced current density of about 10 to the 16 amps per meter squared. So just for reference, that's similar to the current densities that are achieved on the Z machine when you implode a maglev liner. So again, this is a simulation where we haven't included any MHD in it, but just the alpha flux itself and the way it interacts with the electrons should be sufficient to generate really large current densities. So really, with this piece of work, we've stated, well, we think that this is the effect the alphas will have on the electrons. We think it should be incorporated into the macroscopic models, but we're not yet certain what the impact of that may be. So, just going back to it, does a current density of this large, would that affect, the dynamics of burn? Or is it the fact that this is such an extreme environment anyway, it's just so hot and so dense that actually a current of this value isn't going to have any real effect on how it evolves? It's a question that remains to be investigated, but certainly, this is a fairly significant number. Okay, so what we have done with this model is essentially we say, well, we know this collisionally induced current can be generated. What we've done is we've essentially incorporated it into the induction equation, which could be used in fluid models or in MHD for telling you how a magnetic field evolves. So I've written this out in all its glorious detail. Just to go through this is quite complex, but just to highlight, there is terms for the advection of a B field with the fluid velocity. There's the Biermann battery, which we mentioned earlier. There's thermoelectric effects, which we will come back to later in this talk. There's something called the Hall term, which is the J cross B, the effect of the J cross B on transporting magnetic field, resistive diffusion, and finally here in red are these new terms that we've been looking at. So this here, JE alpha, represents the collisionally induced current that is distinct from JT representing the total current in our plasma. So basically we're able to characterize this collisionally induced current such that this is how it appears in our induction equation. Now for our purposes, we can say, well, if the magnetic field is zero, then this equation reduces down to just this set here. So there is the Biermann battery, which we looked at earlier, but also there is a term from the collisionally induced current that even if the magnetic field is zero, this term is not zero. So what that means essentially is that the collisionally induced current itself could generate a magnetic field in an unmagnetized plasma. And I've just put some, very rough numbers into that using this value of 10 to the 16 amps per meter squared, assuming a length scale of 10 microns, temperatures of, of the order of 1 to 10 keV, densities of 10 to the 31 particles per cubic meter. And what you can come up with is a field generation rate of 10 to the 13 to 10 to the 15 Teslas per second, which might sound significant, but if your plasma only burns for the order of, let's say, 100 picoseconds, then, that might only be giving you hundreds of Tesla magnetic field. So, that may not in itself be a substantial amount of field, but nevertheless, it's another mechanism in addition to the Biermann battery, whereby you might be generating magnetic field in an implosion that is initially unmagnetized. Okay, so now I'm going to move on to kind of the second set of results of what we've been looking at. And this is looking at how the magnetic field is transported if the plasma is propagating, if the thermonuclear burn is propagating from hot to cold fuel. So what we have done here is we've essentially come up with a toy model for looking at how burn propagates from a hot fuel to a cold fuel. And in fact, yes, so this is the model we're working with. And I should say, so the details of this are in this archive preprint. We just got the reviewer's comments back on this, and one of the reviewers is quite amused that this is our toy model, and yet it takes us quite a few pages to explain the toy model. So I won't dwell on all this in detail, but essentially what I'm going to say is we've tried to come up with the simplest 1D model that tells us how thermonuclear burn could propagate from hot to cold fuel, whilst keeping all the physics relevant to magnetic field transport that we think is important. Okay, so first of all, for reasons of simplicity, we're using an isobaric condition instead of a momentum equation. So we're balancing thermal pressure and magnetic pressure. What that means is we can only look at regimes of deflagration rather than detonation. So we're somewhat limiting ourselves to those regimes, but this has provided us with a platform for which we can start thinking about the more integrated problem and whether detonation could be important. I'll skip the induction equation for the moment. Then in terms of the DT fuel energy equation, you know, we have to consider the effects of magnetic field transport in that. So we have these various terms here. And then most importantly, obviously, we have the effects of alpha heating, and also we've some bremsstrahlung losses. And then finally, we have this alpha energy transport equation, which is essentially a single group alpha energy transport model, but it is magnetized. So we are able to see the effect of the magnetic field on the alpha particles as well. And so we do that. So as I say, it's in 1D planar geometry. Also, in all these plots I'll show, we have made it dimensionless in time and space, where we're normalizing to the slowing down time of alpha particles in the hot fuel, and the scale lengths are the mean stopping distances of the alpha particles. And essentially, this is, you know, the sort of setup we look at is we have some cold dense fuel next to some hot, already ignited and burning fuel, and we look at how the burn propagates into the cold fuel. So our induction equation in 1D, so what I showed earlier was the full 3D one. In 1D, we need only consider advection, resistive diffusion, Nernst, and alpha flux effects. The Hall term and the Biermann battery disappear because it's geometry. We can also ignore the resistive diffusion because essentially we're in a regime in which thermal diffusion will dominate over magnetic diffusion. So really, what we're seeing is competition between advection, Nernst effect, and the alpha flux effect. And the Nernst effect here, for those who aren't familiar with it, is essentially a thermoelectric term whereby essentially there is an electron current that can move or down temperature gradients and transport magnetic fields down temperature gradients. So we think that this can be quite important in ICF implosions because we form such large temperature gradients in an ICF implosion. Okay, and I don't think I'll dwell too much on this slide other than to say that essentially when we analyze, we look at the nuts and bolts of the transport coefficients. So essentially everything that our collisionally induced current term lives in this gamma now. When we look at the details of that, what we find is that actually, you know, the coefficient for transport due to the collisionally induced current can be similar in magnitude to the coefficient for the Nernst term. But we'll see a better illustration of that later. I'm just returning to this plot I showed of the self-generated fields from Chris Walsh, and I've just added a third diagram here on the right, which I didn't have previously. And what this is showing is the values of the Hall parameter for these magnetic fields that have been self-generated by the Biermann battery. And the point that I really want to make is that, you know, whilst, you know, it's hard to know whether 10,000 Tesla is a significant field strength or not. If we look at what the actual values of the Hall parameter is, it's of order unity. So that suggests that the magnetic field is having a non-negligible effect on the transport within the simulation. So what we have done is we have essentially simplified that result from Chris Walsh, and we have set up our 1D planar burn model where we have added on this red magnetic field, which is showing, you know, essentially a magnetic field at the boundary between the hot and the cold fuel. So the right-hand side here represents hot fuel that starts off at 10 keV. The left-hand side is cold, dense fuel. This remains isobaric throughout. So as it gets hotter, it will go to low density. And what we're interested in is how this magnetic field here, this red line, is going to evolve. And does that have any effect on the way that burn is propagating into the cold, dense fuel? So here is a little movie of what happens when we let this simulation go. And you can see essentially there's two interesting things. First of all, we're getting this large spike in magnetic field here. And then later in time, we're getting a second large spike in the magnetic field at this point. And also what we notice is where this second spike in the magnetic field is occurring, we're also getting this really steep temperature gradient, which is what the blue line represents. So what we can do then is we can interrogate that simulation and we can essentially say, well, what causes these magnetic field spikes? What we're finding is that essentially the first spike here is mainly due to this Nernst term moving magnetic field down the temperature gradient. This intermediate region then is due to advection of the magnetic field, because as you start burning into that cold, dense fuel, essentially there's an ablation effect whereby the field moves from left to right, and it is carrying the magnetic field with it. So we're advecting field from cold to hot fuel. And then thirdly, what we find is you get this secondary spike because you have another region in which both Nernst pushing magnetic field down the temperature gradient, but also the alpha flux effect, this collisionally induced current, are pushing field from right to left. And so we are getting compression of the field because it has been moved from left to right by advection and from right to left through the Nernst and alpha flux effects that is compressing it into this thin spike. If I switch off the alpha flux effect, then what I'm left with is the dotted red and the dotted blue profile. So this is really just showing that it is both the Nernst effect and the alpha flux effect that are giving you the very sharp spike. Also, this is the actual alpha flux that we're calculating in the simulation, and that peaks where we are getting the secondary spike. And then finally, I think what's possibly most important is if we have zero magnetic field in this, then the temperature profile that evolves is this dotted blue line here, which looks very different to the solid blue line. And essentially what we can say is, well, if this simulation was unmagnetized with no magnetic field, first of all, we would propagate further into the cold fuel. So, you know, we burn further into the cold fuel. Also, we have a much less steep temperature profile. We don't get these regions with these really steep temperature gradients. And that's essentially because we're suppressing the electron thermal conduction and also the alpha transport because of this magnetic field that we're forming this very steep temperature gradient. And that becomes more clear if I take this same simulation and instead of illustrating the magnetic field, I look at what the Hall parameter does. So this is the exact same setup, and that magnetic field corresponds to this Hall parameter initially. So there's a peak value of about 2.5. I'll now let the same simulation evolve, but with the Hall parameter move instead of magnetic field evolving. And what we can see is where that second magnetic field spike was formed, the Hall parameter grows very, very rapidly, and it has increased by about an order of magnitude by the time this simulation ends. Now, if we look at the starting and finishing values of the Hall parameter as a function and what values of thermal conductivity they give, we can get this sort of plot shown here in the bottom right, whereby our coefficient for thermal conductivity, kappa C, has gone down almost an order of magnitude because of that increase in the Hall parameter. In terms of the actual thermal conduction itself, what we are seeing is that there is a substantial decrease in the thermal conduction because the Hall parameter is increased. Now, Hall parameter, as I said, is a measure of the magnetic field, but it's not just the magnetic field strength. The Hall parameter is also increasing because the fuel is getting hotter. Okay, so this is what our thermal conductivity looks like, where the kappa C from this plot is, you know, it's multiplied by density, temperature, and the electron-ion collision time. So even if the magnetic field is constant, but your plasma is heating, then that is going to change what the thermal conductivity is. And so what these plots that I'm showing here on the left are showing is what the thermal conductivity is if you had a purely unmagnetized plasma, shown by this dotted line here, versus if you have some magnetic field that is constant, but the temperature is changing. So essentially the dotted red line is increasing with about T to the 5/2. And if we look at the blue lines, then temperature there is also increasing, but essentially because the temperature is causing the Hall parameter to increase, you reach some value of the Hall parameter somewhere close to 1, whereby the thermal conductivity is actually going to start decreasing as the plasma gets hotter rather than continuing to increase. So essentially, regardless of the field strength that you start out with, as you heat up the plasma and as it starts to burn, you're going to find that you can be reducing the rate at which the thermal conductivity increases compared to if it was fully unmagnetized. Okay, so essentially I can see now, just checking the time, that I don't have too much longer, so I will just quickly skip through some of these slides, but really we're making the same point in these slides, except what we're doing now is that we are, instead of starting off, so in the previous slides I simply had that field that was localized to the initial burn front region. Whereas here, what I'm doing is I'm actually setting a uniform value for that Hall parameter initially, such that we can understand better how the transport is evolving. And with this, we see a similar behavior. So these are the temperature profiles that we get. So the solid red line here is the temperature profile when we have that initial uniform Hall parameter, and comparing that, if we have assumed zero magnetic field, we get this dotted red line here. And so again, we can see that there's very different shapes between these two temperature profiles. And again, the unmagnetized one has propagated further into the cold fuel than the magnetized one. And the magnetized one is also, it's much steeper, and it's forming this region here of quite a steep temperature gradient. And that corresponds to where our Hall parameter is growing fastest. So in this particular simulation, this particular slide, what you're looking at here, the solid blue, is what the value of the Hall parameter is after the temperature profile reaches this state. And essentially, what we're seeing is that where the temperature is increasing most rapidly is also where the Hall parameter is increasing most rapidly. But that also means that we're suppressing the thermal conduction most rapidly in that region. So what I'm actually going to do, and again, we can, I've quite a few slides here that just show how the B field transport is evolving in this regime, but it's quite similar to what we see earlier, that there's a mixture of advection, Nernst, and alpha flux effects. But what I want to finish up with, I think, here is this particular slide, which I know in this seminar series, possibly a few weeks or a few months ago, Louise Willingdale gave a seminar that was talking about double ablation fronts being formed in experiments of a laser heating up a gold foil. And I have taken this image up here from the paper from, I think, Paul Campbell that reports on those results. And essentially, there's kind of an analogy between what we're seeing in this propagating burn model with their double ablation fronts, in that we can say, well, we have, a region here where we're forming a steep temperature gradient due to alpha heating right at the burn front. But also behind that, we have a second region of a very steep temperature gradient whereby we're suppressing the transport due to the magnetization increasing so rapidly at that region. So, I think there's sort of a nice analogy between those two results. And so essentially, what we see, the cumulative effect of this is that the magnetic field transport at the burn front and the suppression of the energy transport can reduce the rate at which you burn up the cold fuel. So this is a result that, I think, so there is this kind of seminal paper on this from Jones and Mead from the 1980s. So the effect that burn propagation is suppressed by a magnetic field is pretty well known. But I think what we're illustrating here is that the actual dynamics of the magnetic field transport and how that burn propagation evolves can be quite different when you have a magnetic field present, which might warrant further study. So I guess here is the conclusion slide. So, I think with this, we probably have three main results that we think are interesting. We have quite a lot of work to do to work out, well, just how significant are these results? How do they interact with other things like, instabilities? What do they look like in 2D or 3D? And probably most importantly, we've looked at a toy model for burn propagation. Are the effects we've seen, are they going to be significant if you have an actual spherical or cylindrical target? So clearly there's a lot of work to do, but, just illustrate some of the interesting physical processes that could be occurring in a burning plasma. So thank you.
Thank you very much, Brian. That was a very nice talk. So please enter your questions in the chat field. And also in the meantime, I will welcome everybody to unmute yourselves so you can give Brian a nice applause and thank him.
Thank you.
So there are already a couple questions and comments in the chat field. So Omar Hurricane says, seems like you're describing an ignition and propagation of burn. We generally use the term a burning plasma as a lesser state where alpha heating is roughly the same size as input PDB work, but it hasn't ignited yet. I think that was mostly a comment.
Yeah, so I think in this second half where we are very much considering some regime where you are propagating burn. I would say with the original one, with the collisionally induced current, the alpha, I think, the alpha, it's doing some estimates of the estimated alpha flux in, say, I think I did the numbers for the HDC experiments. And I think you're still able to generate, if this theory is correct, you're still able to generate current densities of the order of 10 to the 15 amps per meter squared in those experiments.
Okay. And Ed Hartooni asks, what is the estimated energy in the magnetic field?
I'd have to check the actual numbers. We are looking at regimes where the magnetic pressure is small. So I should have said that. One of the assumptions with the propagating burn model is that the magnetic pressure is still small relative to the thermal pressure. So really, the effects of the magnetic field are the effects it has on the energy transport, the thermal conduction, and the alpha transport, not on the magnetic pressure changing the fluid dynamics.
And there's a question from Paul Springer. Won't 3D effects break up the sheath of the magnetic field?
Yes. So I guess, the basic idea is like, well, if you had a purely spherical ignition and you had an alpha flux of 10 to the 35 particles per square meter per second, and it was fully isotropic, then you cannot have a fully isotropic current. So yes, it would. I think there would have to be some mechanism where it would break up. But again, that's something we're interested in thinking about more. Is how would that evolve?
And I had a question. So when you're showing the perturbation on the Maxwellian due to alpha particles, first off, I thought that was rather neat. And I was wondering if you considered whether collective effects might be important and whether those were captured by the way you treated that in terms of producing electric and thermal currents.
So we didn't consider it, but I'm not going to say that's because we didn't think it was important. So really our starting point was we decided, well, we know how classical MHD transport works. Can we treat the alpha population as a driver of transport? So I think that's something we should look at. And really, what our motivation here was saying, well, even if we can assume that the electron collision time is significantly faster than the electron alpha collision time, it still may not be safe to ignore this alpha effect on the electron population. But whether we've accurately captured how those electrons are being perturbed is again part of the future work, I think.
I think I'm glad somebody's looking at that. I think one avenue to go down is just look at the dielectric function using perturbed distribution functions to see how that's altered.
Okay. Yeah.
And then we calculate the quantities with that dielectric function. But anyway, so Steve Hahn has
some homework. Thanks, Paul.
So Stefan said, just to be clear, do you think these changes to the burn front would arise from Biermann battery generated fields in initially unmagnetized implosion?
So I think that's a really good question. In that I just will jump back to it because I think it's probably so these conditions, the starting point here, we do not have a significant magnetic field. I suppose what I'd say, if the Biermann battery theory in the implosion of the ICF capsule is correct, and we can get magnetic fields of order 10,000 Tesla, and they are at the edge of the hotspot, then I would think it's possible that they would have some effect on how the burn would, evolve. So this is like this field here, has really been localized to just the burn front. But because then when the burn starts to occur, you increase the Hall parameter so rapidly, it can suppress that thermal conduction quite rapidly. However, I guess something we don't know is, well, we have this really idealized 1D model. What is happening in the center of the hotspot, we haven't really looked at. So essentially, if your hotspot heating is sufficiently robust to detonate, then it doesn't really matter, what the thermal conduction is doing. At the edge of the hotspot, you will burn anyway. But, what may occur is that these magnetic fields are sufficient to keep more energy in the hotspot than you would think if you ignored them.
Chris Walsh says, if we get to propagating burn by making the hotspot more symmetric, we would expect lower magnetic field strength.
That's true, yeah. So again, I guess with his estimates, he's generating really large perturbations to get to these magnetic field values of, 10 to the 4 Tesla. So that is true. If you have a symmetric implosion, you've no Biermann battery to generate the field in the first place.
Okay, any other questions or comments? And if not, let's thank our speaker again.
Thanks, Brian.
Thank you.